Hey everyone. In this video, we're going to be looking at aldehydes and ketones. But before we get into that, let's take a step back and talk about the carbonyl group. So the term carbonyl refers to a carbon-oxygen double bond. And so just this portion is a carbonyl. Now, carbonyls are a common functional group, and they are a part of these five different functional groups. So all of these have a carbonyl, but what distinguishes them from one another is what is attached next to the carbonyl. So let's talk about the polarity of a carbonyl real quick. Oxygen is very electronegative, much more so than carbon. And so we have a strong dipole going towards the oxygen. And so we would say that the oxygen side is partially negative and the carbon side is partially positive. So it's a very, very polar bond. Now, all of these have this carbonyl here, but what distinguishes them is what's next to the carbonyl. So aldehydes have a hydrogen. Ketones have carbons on both sides. The ester has an oxygen and then another carbon. The carboxylic acid has the OH here, and an amide has the nitrogen. And so those are the key characteristics to distinguish these five functional groups from one another. And so for the rest of this video, we'll be focused on the top two here, the aldehydes and the ketones. So essentially, an aldehyde and a ketone are the two carbonyl functional groups that don't have any other types of atoms. The oxygen is the only non-hydrocarbon in the molecule. Now, for an aldehyde, the carbonyl is at the end of the chain, and for a ketone, it's somewhere in the middle of the chain. And so if I had a long molecule and I wanted to put a carbonyl on it, if I stuck the carbonyl at the end, it would be an aldehyde. If I stuck the carbonyl somewhere in the middle, it would be a ketone. Otherwise, they're pretty much the same thing. Now, drawing these, you can draw it as condensed or expanded or as a skeleton structure. Now, I will probably draw them as skeleton structures on your exam, but your textbook likes to draw them as these condensed structures. And so your textbook uses the abbreviation CHO for an aldehyde. And so highlighted in pink here, you can see the CHO. And so if you see that, that means the same thing as this. And they abbreviate ketones as just CO. And so it's implied that there's a double bond to the oxygen. I won't do this to you on a quiz or an exam, but your textbook does that a lot. So just in case you see that, now you know what it means. I will primarily give these structures to you as a skeleton form. All right, let's do a quick check. Can you classify each of these as an aldehyde or a ketone? Well, the first one, A, we see the carbonyl is here, and it's bonded to a carbon on both sides, so that's going to make it a ketone. For B, we see that there's a hydrogen next to the carbonyl, and so that's going to be the aldehyde. For C, there's another hydrogen next to the carbonyl, so that's going to be an aldehyde as well. Oops. Aldehyde. And D, we can see that there's carbons on both sides of the carbonyl, so that's going to be a ketone. Now, for drawing aldehydes as skeletons, in order to emphasize that it's an aldehyde, we usually include the hydrogen that's attached to the carbonyl. Now, you don't have to. It's okay to draw it this way at the bottom. This is technically correct because in a skeleton, you don't draw any of the hydrogens that are attached to carbon. So this is totally fine as a skeleton, but most chemists draw the H in just to emphasize that it's an aldehyde. But if you do it this way, totally fine. All right, let's talk about how to name aldehydes. So we're going to use the same rules for naming alkanes, except we're going to change the E ending to AL. AL is for aldehyde. Okay. So one carbon would be meth. So this would be methane now. Two carbons, ethanal. Three carbons, propanal. Four carbons, butanal. Let's try and name this one. So we want to number the chain here. And the aldehyde is always number 1 because the aldehyde is always at the end of the molecule. And so 6 in a row, we would say hexane, but because it's an aldehyde, we're going to drop the E and turn it into an AL, so it's hexanal. And it looks like we've got something sticking off of carbon 3 here. That looks to me like a methyl group. And so we would have 3-methyl hexanal. Now, you don't need to include the number 1 for the location of the aldehyde because aldehydes are always number 1. So just 3-methyl hexanal. All right. Can we draw the structure of 5-chloropentanal? So we're going to start with the parent, pent. So pent means 5. So 1, 2, 3, 4, 5. And then we need to make the aldehyde at the end. So there's our pentanal. And then coming off of carbon 5, there is a chloro group. So stick a chlorine there off carbon 5, and we're done. So once again, name it just like you would an alkane, but turn the E into AL for aldehyde. And when you're numbering these, the aldehyde is always number 1, but we don't have to include the number 1 in the name. Okay, let's talk about naming ketones. So for ketone, we're going to drop the E, and we're going to add "-one" for ketone. Now, because ketones occur in the middle of the chain somewhere, you have to specify where. And so you're going to add a number for the location of the carbonyl. So this one here has 5 carbons. This would be pentanone. And the carbonyl is at carbon 3, so it's 3-pentanone. Right? If we had this molecule here, it would also be pentanone because it's 5 carbons, but the carbonyl is at carbon 2. So this one would be 2-pentanone. And so that's why we have to specify what the number is, because the carbonyl could be anywhere in the middle of the chain for a ketone. Now let's try to name this one. We want to number it, and we want to have the lowest number possible for the ketone. So 1, 2, 3, 4, and 5. So that's going to be pent and one. And the carbonyl is at carbon 2. So that's 2-pentanone. And then it looks like we have a methyl group here at carbon 4. So 4-methyl 2-pentanone. All right, let's try and go the other way around. If we're given the name, can we draw the structure? So this one here, hexanone. Hex means 6 carbons. So 1, 2, 3, 4, 5, 6. And we need the ketone at carbon number 3. So I'll draw it pointed down there. Doesn't matter if you draw it pointed up or down. Same thing, because molecules can flip around as long as it's attached to the right number. And for the second one here, I see a butanone. But means 4 carbons. So 1, 2, 3, 4. And the butanone is at number 2. So 2 here, I'm going to stick the ketone. And then at carbon 3, we have a methyl group. So 3-methyl 2-butanone. All right, the last thing we're going to talk about is solubility. So as we mentioned previously, the carbonyl is polar, and so it can participate in hydrogen bonds with water, only as the acceptor. So there's lone pairs on the oxygen here, and those lone pairs are pointed directly at the hydrogen. And so it lines up with the partial positive of the hydrogen side and the partial negative of the carbonyl. And so you get that opposite charge attraction hydrogen bond here. And the same trend follows that we saw with alcohols. The more carbons, the less soluble. So aldehydes and ketones with only a few carbons are usually soluble in water. But if you get like 4, 5, 6 and more carbons on the chain, they tend to float and they stop mixing with the water. So smaller the carbon chain, the more soluble. Thanks for watching, and I will see you in the next video.